Hello. This last video of chapter 2 is going to be dealing with hydrocarbons and molecular models. So I just want to give you a heads up that this video does contain some material that's not really in the book. It just will help you out a whole lot if you actually watch this video and read the book concurrently to kind of make full sense of these hydrocarbons. And so first thing, as the name should hopefully imply by now, hydro means hydrogen, carbon logistically means carbon, and so hydrocarbons contain only hydrogens and carbons. And believe it or not, you are actually more familiar with these than you actually think because you use them all the time if you drive a car. If you've ever used lip balm, then basically you're just smearing dead dinosaurs all over your lips. But as long as they come out shiny and stay moist, it works out perfectly. And so, when we talk about naming hydrocarbons, a lot of students way overthink this concept. And so, I just want to tell you now just take a deep breath and just work through these two steps, and you will be fine. And so, the first half of a hydrocarbon's name is going to be the same kind of idea as before with the molecular compounds. They need a prefix to tell you how many carbons. Unfortunately, it's not the same prefix as the molecules. And so for these ones, they have their special, or some of them are special, and especially the first four of the meth, eth, prop, and bute. And so pentan, hex, and het, octanol, and dec, those kind of like can be figured out. But you need to know those first four because they're going to pop up a whole lot in the chem, like especially when we talk about hydrocarbons. And so the first half of any hydrocarbon's name is going to be the prefix. That prefix tells you the number of carbons inside of your hydrocarbon. The second half of the name is going to be the suffix, and that is going to tell you what kind of bonding you are looking at inside of this hydrocarbon. So keep in mind, hydrocarbons are always going to be molecules. They're always going to be covalently bonded. And so if you have all single bonds, you're going to be looking at an alkane, or your ending of the name is going to end in ane. If you're looking at something that contains even just a single double bond, that's horrible to say, even just one double bond, you're going to be looking at an alkene, and the ending of that or hydrocarbon is going to end in ene or an ene. If you're looking at something that contains even just one triple bond, you are now looking at an alkyne, and again ends in yne. And so, for example, if I have something that has 6 carbons in it, you know right off the bat it has to begin with hex. If I tell you it's 6 carbons and all of them are single bonds, you are looking at hexane, ending in ane. If somehow it is indicated that you're looking at even just a one double bond inside those 6 carbons, you're looking at a hexene. If you know that there is a triple bond anywhere in that compound, you're now looking at hexyne, yne. And so in this case, the naming is not the difficult part, but trying to go back and forth between the naming and the chemical formula, that's when some students kind of get a little bit tripped up. And so this portion, it might be in your book, I can't remember, but it's a really good kind of shortcut method in order to figure out these chemical formulas. And so we call these the N+2 rules, or I do at least. And so if you're looking at your hydrocarbon, and again, this is very useful if you're given the hydrocarbon's chemical formula instead of the name, and you're told to name the thing. And so if you look at the hydrocarbon, you're going to have some carbons and some hydrogens. If you assign the number of carbons to n, and what I mean by n, I'm just saying number of carbons equals n, then the number of hydrogens is going to be 2n+2 for alkanes. If you do the same thing and you calculate the value or the number of hydrogens as just 2n, or just twice the number of hydrogens as there are carbons, this has to be an alkene, and it has to have a double bond somewhere in that structure. If you do the same thing and you calculate the number of hydrogens is 2n minus 2, or twice the number of carbons minus 2, like 2, then you're going to be looking at an alkyne, and it has to have a triple bond somewhere in there. And if I did not confuse you enough, here is some more examples that hopefully will help you out. So if we have something like the chemical formula C5H12, you can go through and draw that structure out, which I will and I'll show you, but on a very quick shortcut method, you just have to do a little bit of math. If if you have 5 carbons, then 2 times 5 would be 10. In this case, we have 12 hydrogens, which is 2 times 5 plus 2. And because of that, we know that there are 2n plus 2 hydrogens to carbons, and so we know this has to be an ane. And so in this situation, since we have 5 carbons, it's pent. Since we know we have all single hydrogens, it's going to be pentane. And so now you're probably asking me, how do I know it has all single bonds? I'll show you. And so, first thing is you have 5 carbons. And so I'm going to draw these carbons out like this. And the main reason why I'm kind of staggering them like this is because the hydrogens need some space to spread out. In addition to that, if you drew it as a straight line, then it really would be kind of confusing on where your carbons are and everything else. You may see it in some biology and chemistry books written like that, but again, most organic chemists will write it in this little staggered version. I'll show you why here in a minute. And so, the main key ingredient of being a carbon is that you are going to make 4 bonds all the time. And again, I will explain all this stuff in later detail in later chapters, but right now you just need to know that carbon's special favorite number is 4. And so if you kind of see how I draw it like here, each one of those carbons has to be attached to its neighboring carbon or this molecule would completely fall apart. And so if we just attach each of the carbons, we are now using a single bond to connect each of the carbons. If you take a look at the carbons on the either end, I told you the magic number is 4. In this case, this carbon is only using one of its positions. Same deal with this one, it's only using one spot. And so since we know this is a hydrocarbon, the only thing that's available to fill in these blank spaces are hydrogens. So we know each of these carbons on either end here are going to need 3 hydrogens. So this carbon will have 1, 2, 3, 4 bonds, and this one will have 1, 2, 3, 4 bonds. But additionally, when you look at these carbons in the center, this carbon is already creating 1 bond to the carbon on the left and 1 bond to the carbon on the right. Same deal with the one in the center, same deal with the one right here. And so in this case, you don't have 4 spaces available anymore. You have 2 spaces available. Therefore, you're going to fill in those 2 spaces with hydrogens. So now if you go through and count, we have 1, 2, 3, 4, 5 carbons. And we have 3, 5, 7, 10, 12 hydrogens. And so in something that, again, contains everything is just carbons and hydrogens, you can imagine as an organic chemist, you would be really sick and tired of drawing C's and H's all day long. So another way you might see the structure drawn out is just like this with a bunch of lines. And so in this case, each one of the ends of the lines represents a carbon with the correct number of hydrogens in order to fill everything out appropriately. And then in this case, because this one's on an end with nothing, you know this is only 1 bond, so this has to have 3 hydrogens on it. Same deal with this. With these guys who have a peak, this is going to be a carbon-carbon bond here, but it's also going to be a carbon-carbon bond there, so you only have 2 spaces available there. So, let's get a little fancy. Say we go from C5H12 to C5H10. And so now in this case, you're still looking at a pent, but because if you do the math, 2 times 5 is 10. And so the number of hydrogens in this compound is equal to 2 times the number of carbons. So therefore, you know we're looking at something that has to have a double bond in there, and we're going to call this pentene. But we run into a problem. If we put a double bond between these 2 carbons, like I did with this purple line here, we have too many bonds formed on this carbon on that carbon. So I told you the special favorite number is 4. This carbon has 1, 2, 3, 4, 5. Same deal with this one. It has 5 lines drawn around it. So what we have to do to get rid of it is drop 2 of these hydrogens out of this entire system. And so now these carbons are back to being nice and happy. 1, 2, 3, 4. This one has 1, 2, 3, 4. And we would illustrate that on our little stick model as just drawing an additional bond between those 2 carbons. And last but not least, what if we have C5H8? So here, still looking at C5 or a pent. But here, if we do the math, we have 2n minus 2 equals the number of hydrogens, which illustrates we're looking at something as a triple bond, or we're going to call this pentyne. Now, if we throw in that triple bond, or this green line sitting here, same deal as before, we have way too many bonds on both of these carbons. So the way we get rid of all that additional stress is we drop these two hydrogens out of the system. And now we're looking at 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Or we illustrate this in our stick model by drawing 3 bonds between those two carbons. So hopefully that makes a little bit more sense when you start talking about the enes, the anes, and the yans. Please just pay special note on how these things are actually drawn out. Another problem comes into play whenever you start talking about multiple compounds that can technically have the same name. For example, here we are looking at pentene and hexene in both of these cases. But the problem kind of arises that this hexene on the left has the double bond between this first carbon and that second carbon. This hexene here has the double bond between carbon number 3 and carbon number 4. And so the problem with this is you need to understand, or I guess you need to illustrate which one of these complexes you're talking about, because they do have different double bonds, they have different what we call chiralities, and so therefore they're going to have different chemical properties to them. And so the way that you distinguish between the two is you actually kind of use a number system. And so the first rule here is you start numbering your carbons closest to the double bond. So therefore, in this first one, the double bond is on this far left side. So I'm going to start numbering my carbons starting on the far left side. Here, the carbons or the double bond smack dab in the center, so it doesn't really matter which way you start off. But if the carbon was, again, say it was on this bond right here, then you start counting on this carbon 1, 2, 3, 4, so on and so forth. So in both of these cases, you're going to start off, well, I did personally, I start off with a carbon all the way on the left side because, again, it's the one that's closer to the double bond. As I stated, if the double bond was between the 4 and the 5, then you'd have to switch your entire counting method because now the double bond is closer to this carbon, which would make it 1, 2, 3, so on and so forth. So once you have these bonds, or once you have these carbons numbered properly, the way you name the actual complex is going to be the same in both of these. These are both going to be hexenes. We're looking at something that contains 6 carbons and a double bond. The way that you distinguish between the two is put a number in front of the name that tells you where this double bond starts. So in the first one, we're looking at the double bond between the 1 and the 2. On the second example, we're looking at a double bond between the 3 and the 4. So you're going to use the bond or the number that the bond starts with in order to name the specific hexene. So one on the left is going to be 1 hexene because the double bond starts on the first carbon. If it starts here, we're looking at 3 hexene because it's starting on this third carbon going up to the 4th. Say the double bond was between 2 and 3, then this would be 2 hexene. Note, you will never have something like 4 and 5 hexene. And the reason for that is because if it was between this 4 and the 5, you'd have to switch your number system. And so the only ones you can have for hexene would be 1, 2, and 3 hexene, because 4, 5, and 6 is the exact opposites of the 1, 2, and 3, if that makes sense. So please take a look at the nomenclature when it comes to the hydrocarbons. I am going to have a few videos and practice, websites that I found posted on Blackboard. So go through those, and if you have any questions, please bring them up to me, starting now, because if you wait too long, it's going to be a little bit more difficult to kind of come back to where you need to be. So, last thing we need to talk about when it comes to the end of Chapter 2 are these molecular models. And so, when it comes to chemical formulas, the only thing that a chemical formula will tell you, by chemical formula I mean H2O and CH4 and all those, the only thing that a chemical formula will tell you is the number of atoms. And so again, if you're given a chemical formula, they don't tell you how those atoms are arranged. They don't tell you if there's any spaces between those atoms. They don't tell you about any angles, nothing that has to do with the three-dimensional world that we live in. And so if you want to know anything about these actual structures, you have to get a little bit more creative in how you write these things out. And so the first way you can kind of write it out to get a little bit more information is what they call the structural formula. And so H2O2, if you look at the chemical formula and just the formula itself, if you have no knowledge of chemistry, you would think that those two H's are attached to each other and those two O's are attached to each other, just because we group them up whenever you start writing out these formulas. But please, and I'm asking you from now until the end of your chemistry career, never, ever, ever give hydrogen more than one bond. It just can't happen. And so writing out a structural formula shows you a little bit more detail on how these things are actually connected to one another. Same example with CO2. Whenever you're looking at this, you are not going to just have a carbon and then an oxygen in the center of a carbon and an oxygen. Here you actually have the carbon in the center, and the two oxygens are actually 180 degrees away from both of those. But just looking at the chemical formula will not give you that bit of information as you kind of just look at it. In that case, when we start talking about models, even a structural formula has its drawbacks. The main drawback is you're drawing this on a two-dimensional screen or on a two-dimensional piece of paper. If you draw something like CH4, the only way you can really draw it out is in that cross shape. But again, that is definitely not how CH4 exists. So if you want to know a little bit more information about how these molecules exist in a three-dimensional representation, you will go to the good old ball and stick model. And so you can usually buy these at most like stores or even like science stores. And the cheaper versions, I mean, they have like plastic ping pong balls that are colored and like straws for the sticks. But you can get more expensive versions. But basically, all it really comes down to is the balls are going to count as atoms and the sticks are going to be the bonds. So I think it's safe here that I need to reiterate atoms are not spheres. They do not look like atom or like marbles, but for lack of any other representations, these work out pretty well. And so whenever you use a molecular model or ball and stick model, they actually show you how these atoms would separate between themselves in a real 3D environment. And the last one is the space filling model. I just kind of call this one the ball and stick model on steroids. All it really does is just kind of expands all the spheres so they kind of smash into each other. And this actually represents how things truly bond. It's actually an overlap of these electron clouds. But we'll save all that until like chapter 10. And so, quick representation. As I stated, molecular formula for CH4 will tell you that there is one carbon and four hydrogens. It really doesn't tell you how these things are orientated around each other. But if you were to draw out the structural formula, you would see that the carbon is in the center, and each one of these hydrogens has a single bond to that carbon. But again, that is a two-dimensional drawing. If you were to take this thing off of the board or out of the screen and put it into the three-dimensional world that we live in, you would actually see that each one of those hydrogens separates as far as possible from the others. And so this is no longer just a completely flat cross. Now this is what they call a tetrahedral geometry, and each of those hydrogen-carbon-hydrogen bonds, or I guess is going to be a 109.5 degree angle. And the space filling model, as I kind of mentioned, it's just they expand all those spheres until they are overlapping, which actually more specifically shows how these things kind of orientate themselves. All right, everyone, that's all I got for chapter 2. So please be on the lookout for chapter 3 coming up soon.